And here we go. So I would like to introduce the next speaker, who is Sergei Nechaev, who will speak on some problems of extreme statistics, or random walks and random operators. Please go ahead.
Thank you very much. And I would say that probably you will consider this talk a bit eclectic. And please don't hesitate to ask me the questions just during the presentation, okay? So I will try to go. Okay, so the problems considered in the talk I mentioned here. I will start with some questions related to statistics of so-called stretched random walks above some curved boundaries. So then I will pass to statistics of one-dimensional random walks in a Poissonian field of traps, and I will try to convince you that there is similarity between 1 and 2. Then I will go to spectral properties of random operators, like related to Anderson localization in one dimension. And if I will have time, I will end up mentioning the connection with phyllotaxis. What is that? I will remind you later. Okay. So let us start. And this is the first topic, subtopic, stretched random path over semicircle. And it's very easy to understand how the model is formulated. You have, say, semicircle, and you have random walk in the whole plane, which starts here and ends here. So just near left boundary it starts, and here it ends. It has n steps, and the condition is that the random walk is stretched. So in this, it is stretched in the sense that its length is, if you are on the lattice, is much easier to formulate. The length of the trajectory doesn't deviate much from the boundary. So I would say that the length of the trajectory, red trajectory, is comparable to the length to the half perimeter of the circle. So, and then we will ask the question about the span of this red trajectory, so the how it deviates from the boundary. And I will try to show you that there is some surprising and, to my point of view, rather interesting and unexpected scaling behavior, which okay, so I will show you later. I will not mention right now the answer. Similar problem, which mentally is related to this model, is like that. So you have the channel, two-dimensional channel, where you have non-uniform, when you have such bumps. So periodic or non-periodic doesn't matter. We will pay attention to the random walk, just to the behavior on the random walk, just near, for instance, only one such bump. And the random walk has a drift. So it means here are the jumping probabilities. So with more probability, you can jump along along the channel, and with smaller probability, you can jump back, and you have equal probability to jump up and down. So, and then the question is the same. You begin your random walk in points A, B, or in some other points in between, and then you look how this random walk, how this red trajectory penetrates the shortest path, shortest slit between these curved shapes. And there is some unexpected behavior which I will mention later. Okay, the reason why I'm talking about that, probably you will see later, because all these questions rather unexpectedly are related to some ultrametric behavior of random operators. But this will be mentioned in the next section. Okay, so first, as I have mentioned, we have two-dimensional random walk, which starts in point A, ends in point B, has n steps, and here we have inserted the gray semicircle, which serves as a boundary. Inside this random walk cannot penetrate, so it winds around it. And the question is, what is the span of this random walk about the tip of this semicircle? So the distance d, which is mentioned here. Let us suppose that the trajectory is very, very long compared to this inserted semicircle. So I would say that even larger. So n is the number of steps, and r is the radius of the semicircle, and this is the typical scale. So it means that the trajectory is very, very long compared to this bump. So then this span will be just square root of number of steps, because trajectory doesn't fill this inserted semicircle, and it's like a random walk. But now let us stretch the path. Let us consider trajectories which have such scaling. So the number of steps scales in the same way as the length of the boundary. What would be your expectation how this span would behave? What would be your guess? Do you have any ideas? Will this scaling change or not? Okay.
Of course.
Huh?
Square root of the of n.
No. You see, it's rather it's scaling which seems rather unexpected. So the stretch trajectory, the fluctuations of stretch trajectories behave like 1/3 of number of steps. Why? I will explain on the next slide. But now, next model, which is similar but slightly different. The difference is that here we have inserted not the semicircle, but the triangle. Yeah, and the question is absolutely the same. We have the random walk, which winds around the triangle, and we ask the question about the span of this random walk. And first is the same, of course, and the second. So what do you think? How the stretch trajectory will behave over the tip of this triangle? Okay, so the answer is that is constant. So you see that
N power 1/3.
Sorry?
N power is 1/3.
Here is 1/3,
Yes.
but here is constant. It doesn't depend on n at all.
Mm.
Yeah, and so we can see that probably the curvature and the neighborhood of the points near the tip of this point where we consider the fluctuations are responsible for the behavior, because difference between circle, semicircle, and triangle is in the fact that here the curvature is constant, but here is concentrated near the tip. Okay, first, so this is one slide of exact computations. Maybe let me return to it later, because first I would present some hand waving arguments. I will return to this, but just to explain, and then I return to these slides. So how we can get this one-third behavior? So let us consider the points. Let us consider some distance near the tip of the semicircle, where we can replace the curvature by the straight line. So like here, for instance, the Pythagorean theorem. So I consider this segment LM, yeah, X is LM, and then just by the Pythagorean theorem, I can express X, so this X in terms of R square and Y, yeah, and then so this is just from this triangle, yeah. So and then if I consider R much larger than Y, so I can linearize. I can consider only first non-vanishing term. So and then the behavior is like that. So this is one expression between a connection between X and Y, and it tells us where we can linearize the scale on which we can linearize this the surface, making it flat. So and now we can say, okay, since now this segment can be considered as a flat, so above it we have random walk, just one-dimensional random walk, where this longitudinal distance x is like a time and y is like a space coordinate. So we have y proportional to square root of x. So, and this is exactly the signature of the fact that our trajectory is stretched. So this x can be considered as a time. So, and now we can solve these two equations together. So this one, x proportional to this one and y proportional to this one. So, and finally, you immediately will end up with the fact that x is proportional to r to third and y to r 1/3. So, and this is the answer. Yeah. One can generalize slightly this model, for instance, considering non-uniform curvature, but I will not pay attention to that. So, and let me return to the slide which provides more or less rigorous computations. And the rigorous computations are very simple. So you have diffusion equation above, you have diffusion equation above the semicircle, and you have boundary condition, Dirichlet boundary condition 0 for the probability at the boundary, and you have initial condition that your walk starts at some point left and then ends on the right. So, and then everything can be expressed in terms of Bessel function. But now you should take care of special scaling limit, because now since the trajectory is stretched, the dependence on r and on n number of steps and on the size of this the circle are not independent. They should be taken simultaneously. So stretching means that this scaling should be inserted in this equation, and then the probability should be computed. And if you proceed in such a way, we cannot exactly solve this equation, but some other arguments and some other motivations, which I will not present here, show that the answer is expressed in terms of Airy function. And so this is the probability density above the semicircle, above the tip of the semicircle, and the span of this trajectory is the typical fluctuation of this path, and it scales like n number of steps in power 1/3. So here we can see also a phase transition, because it's natural to suggest that if we increase the number, this number c, so then the trajectory becomes larger and larger, and it deviates further and further from the semicircle, and the critical exponent changes from 1/3 continuously to 1/2 to the Gaussian behavior. For a moment, we cannot tell exactly what kind of phase transition is that, but it's rather smooth. Okay, so this is the physics behind this problem, and some interesting connections are as follows. You can do the following. You can play the following game. Let us take the random loop. So this red curve is the loop, and we try to expand it as much as possible. So the shape which corresponds to the maximal area is just the circle. So let us consider this circle as a limiting shape, and then let us make the radius slightly smaller. So we first inflate our trajectory and then slightly deflate, and it starts fluctuating near the typical boundary. What are the fluctuations of this path? We can compute this, and they are Gaussian. So they are Gaussian, and the critical exponent is 1/2, and it's like ordinary random walk. But now we do absolutely the same. So we inflate till maximal shape our trajectory, then slightly deflate it, and insert inside the solid circle. So now the boundary is impenetrable for this random walk, for this random red random path. So each time one can say that this boundary serves as a limiting solid shape for this red trajectory. And now we can compute the same quantity, the span of this trajectory above this boundary. And immediately we end up with the fact that the fluctuations are governed by Airy function, and the typical scaling changes from 1/2 to 1/3. So when you insert nothing, you have very large modes and soft modes in your system, which make your model soft, and the fluctuations still remain Gaussian. As soon as you insert something inside, you prohibit the long scale fluctuations, and the trajectory fluctuates just in the neighborhood of the boundary. And this influences the behavior, and it appears with another scaling. So now I should mention that this scaling 1/3 is nothing else as so-called KPZ scaling, Kadar-Parisi-Zhang scaling, which appears in the non-stationary growth problem. But I should mention the model which about which I said before, and this is the model when absolutely ideologically is absolutely the same. We emit the trajectories from points A or B, and they have preferential direction to move along the channel, and they fluctuate slightly in tangential direction. So, and now we ask the following question. For instance, like in the picture here, what are the typical fluctuations of the path above the near the boundary? And we can see that this distance d is again governed by the scaling 1/3. It's not Gaussian, and this is very, I think it might have some applications, because suppose that these red lines are something like passive scalars, something like trace lines of particles in the liquid. And you have just non-turbulent liquid which moves through the channel like that. And here we have represented the bunch of trajectories where the starting points are in different places across the channel. And the most interesting situation is mentioned in the picture F right here. Look at the profile of the distribution function in the most narrow region. So you see that this distribution function has two maxima at the boundaries. So it means that trajectory, when you emit trajectory and it touches the boundary, then it slides along it, which is reflected in the fact that near the boundary you have a maximum. So the trajectory which go through the channel just in the middle, of course, they don't feel the boundaries, and they have the maxima also. And the trajectory near the upper boundary again have the maxima. So this is very interesting behavior, meaning that the distribution of trajectories across the channel is non-uniform. And if you touch the boundary somewhere, with more probable would be such behavior that you slide along it and not deviate far away. And here is just the profile which is shown here. So we emit the particles from this point, and so then you see that they dissipate, they come to the boundaries, and then they have maxima just at the boundaries. So this is three-dimensional profile of this picture. Okay, so this is something which is, I would say, physical part. And now I can go step by step to the situation where some ultrametric behavior of trajectories appear. So this is the picture again, as here, but now what are these parts, gray parts, which I have mentioned here, which I have shown here? So these are so-called blobs or parts of the trajectory which can be considered as independent. So how the behavior, how this typical trajectory, which doesn't deviate far away from the boundary, behaves. So it starts moving, then somewhere it touched the boundary, and this is so-called of renewal time. So it goes, so then it touches the boundary, then the new process starts again, so then it touches again, and so on. And this is the typical size where these parts are uncorrelated. And one can estimate them, and of course they depend on the curvature, and this longitudinal size can be estimated as so it's square of perpendicular direction. So since the perpendicular direction was r in power to 1/3, so this is power to 1/3. So, and then we can estimate the energy of the stretched path and estimate the probability of such configuration, its Boltzmann weight. Yeah, so the free energy can be estimated as number of such gray blobs. So this is number of steps divided by length of it. So and this is r 1/3, and Gibbs measure or can be Boltzmann weight can be estimated as e to the power minus free energy, and this behaves like that. But now let us make the Laplace transform of this function, inverse Laplace transform, and you will immediately realize that in generating function of this behavior has such scaling, is e to the power 1 over square root of s, which should remind you the Lifshitz scale in Anderson localization. Now there is a question: is it just a coincidence, occasional coincidence, or there is something behind it? And my guess is that there is something behind this. And the next slide, I will just try to tell more about that. So let us come to the statistics of one-dimensional random walks in a Poissonian field of traps. So the model can be shown like that. So suppose that you have so this everything is one-dimensional. Suppose that you have direction as time, when time runs, it's number of steps, and perpendicular direction is the size, is the length of the segment in which this random walk fluctuates. So for instance, D3 is just the thin slit, and the random walk moves along this line, and it fluctuates in size this one-dimensional segment. Here I have shown another absolutely identical picture, but I take the segment bigger, so it's something like that. Please don't pay attention to the fact that this is just one after another. I can draw them separately, but for me it's more convenient to draw them just one under another. Okay, so we have independent random intervals of size d. So this exponential or Poissonian distribution, but I don't care about the prefactor. Yeah, and we have just the question about the we would like to compute so-called survival probability. This is nothing else as the famous Balagurov-Vax or Donsker-Varadan problem, when you have number just ensemble of random intervals. You run on each of it the random walk, and then you ask the question, what is the survival probability that till time t or till number of steps n, your trajectory stays alive? Okay, and this can be estimated very easily, and this is so-called optimal fluctuation estimation. So I have two contributions to the, I can write the free energy. I have two contributions to the free energy. One comes from the localization. So number of steps divided by square of size of the segment when where it fluctuates. And this is nothing else as just the smaller eigenvalue of the if you solve the Schrödinger problem, the smaller eigenvalue behaves like square of size of the system of the segment. Okay, so and the second contribution comes from the disorder, is the logarithm of its probability of having the segment of some particular size d. So taken from this distribution. So logarithm of this distribution gives you the entropic contribution to the free energy. So and now you have to minimize these two contributions. And if you do that, you get immediately the survival probability, which has the scaling exactly the same as I have mentioned before, n in power 1/3. And I repeat that n is the number of steps in the random walk. So if you would consider, for instance, the same problem not in one dimension, but in two dimensions, of course, this 1/3 will be changed. But for me, the situation of one-dimensional random walk is more interesting. And again, as I said, if I take the inverse Laplace transform, we go to the generating function, we get something which is known as Anderson localization. Now, let me compare these two situations. So here in the left part, I have the stretched random walk above the semicircle, and here I have the random walk in the number in the Poissonian in the on the random in the family of random intervals. So of course the optimal fluctuations are different, but they lead to the same scaling behavior. And okay, so I haven't more solid arguments than I have mentioned already, but the idea is such that the situations are similar because here these gray blobs appear in the following way. So we have random walk, so then somewhere it touches the boundary, and then there is a renovation of the process. So it starts from the boundary, then it runs somehow, and then it touches the boundary again. And the typical distance between these touching boundary moments is just the size of the typical size, longitudinal size of this blob. And it behaves, here happens the same. Absolutely, here the situation is absolutely the same. I start from the point A, so then I run, then I touch the boundary, then I go again, forth, and so on. So ideologically, situations are similar, but they are forced with absolutely different. So they here they are governed by different things. Here, this behavior, this 1/3 behavior, is related to the fact that we have random walk in ensemble of channels which have Poissonian distribution. And here we have no disorder at all, but we mimic the same behavior by the curvature. So this scale, longitudinal and tangential scale, is dictated just by the fact that this trajectory is stretched above the circle, while here is just the straight channel, but we have random distribution of these sizes d. Okay, so let us consider these situations in more details. And but first, I would mention where this kind of behavior happens. So what we have considered is this problem when we have semicircle and we run the trajectory above the semicircle, and in this case we have the fluctuations governed by the scaling 1/3. The same, and I would say the original motivation to consider this model is shown here in the first picture. It's so-called family. This is a family of so-called vicious random walks. So these are trajectories which start somewhere in the neighborhood of this point and somewhere here, and they don't like each other in the sense that they cannot. So these are directed random walks. So this is 1 + 1 dimensional system, but they cannot cross. So they don't like each other. And from this point of view, this family of random walks can be considered as a family of world lines of fermions. And the question is about the fluctuations of the top line of the most of this line which encloses the picture. Why these two situations seem similar? Just because here is something like mean field approximation of this model, where I replace the effect of all other lines just by the solid boundary. But of course, I cannot consider in this model the backward effects. So the random walk, this random walk doesn't affect on the boundary of this. But while here there is mutual influence. Similar happens in so-called magnetic dick path. So this is the random walk where you have fixed lengths of the trajectory, and also you fix the area below the curve. In special regime, the fluctuations of this steep top line is again governed by KPZ scaling exponent. And also one can consider a random walk on trees and not on trees of special topology. We call them super trees because it's not uniform tree, but it behaves such that this each time on the next generation you have less and less number of branches. So it's not uniform random walk, but what you can do, you can run so-called Brownian bridge. You can consider a closed path on this tree. So the trajectory which goes somehow along the tree, but then it comes back. So, and again, in special regime, the fluctuations of these Brownian bridges on such non-uniform tree have this KPZ behavior. Okay, now spectral property of random operators. Let me return again to the picture I have shown already. So this is the set of random walks inside the cage of size D3, D2, D1. So I can represent them in a discrete way schematically in the following, as follows. so I can consider the operator such that I have three diagonal operator where I have something, for instance, 0 on the main diagonal, and then I have ones on subdiagonal, but somewhere I have zeros. So somewhere, so here probably is better seen. So I consider the operators of the following form: zeros on the main diagonal, and then x1, x2, x, and so on are random variables, which can be either 1 or 0. 1 with probability p and 0 with probability 1 minus p. Yeah. So then, of course, if you have sequence of ones, so then you have a cage, and then as soon as you have 0, so you immediately split your operator in blocks. Yeah. And what one can do very easily, one can compute the eigenvalues of such uniform subchain in the block. And now the question is, what is the spectral density of such operator? Yeah. So again, we have ensemble, we have family of random operators like that. All x are random variables, 1 or 0, and we consider the spectral density. The physical motivation I already explained, because in some limit we expect that we will get something like Anderson localization. And but to formulate exactly, this is shown here. So we have spectral density, which can be written as typically as delta function. Yeah, so we count how many lambdas we have, and we sum over all cages. Yeah, so here it's shown in more details. So this is something standard. So this is the green function, or if you wish, the regularization of the delta function. So this is the probability of having a continuous set of ones. So this is q p in power d. Okay. So, and this is the exact expression, of this of the spectral density of this operator. Now, first, of course, it would be interesting to see numerically how it looks like. And now, I guess we come step by step to the subject of the conference. So you can see here some kind of ultrametric behavior in the spectral density, and even which is more interesting, it has some number theoretical properties. So first, what we can do, we can see what is the behavior of the spectral density near the boundary of the spectrum, and this is just the behavior I have mentioned in the first part. So how we can proceed? So we can estimate the highest eigenvalue, expanding this cosine. First, what we can see is that all maxima are concentrated just at the positions where this cosine is 0. So, and the main series where the cosine is 0 is 1, 2, 3, 4, 5. So this is the enveloping shape. So, and so therefore we can expand this when d goes to infinity. D is just the number of the size of our system. So, and it turns out that there is a limiting value 2 and some correction. And now we can express d in terms of lambda and substitute it in just the estimation. So d we express in terms of lambda and put it here. So, and we get nothing else as just the so-called Lifshitz tail of one-dimensional Anderson localization. The behavior of spectral density near the spectral edge when p is small. Okay. What we can say more? You know this famous representation of fourth cycle of Fibonacci Fourier sequence by fourth circles. So let me briefly remind it. So you have segment between 0 and 1. You write terminal points as 0 by 1, 1 by 1. So, and then you draw circles which touch each other and touch these terminal points. And then you inscribe the circle such that, again, it touches these two and the boundary. And you proceed so forth. And you ask the question, what are the positions of centers of inscribed triangles, of inscribed circles? And the answer is interesting, nice, I would say. Especially it looks nice for the undergraduates. You should sum the fractions in such a way that you sum numerators and denominators. So, for instance, to find the position of this circle, 2/3, you should sum 1 plus 1 and denominator 2 plus 1. And in general, this generates the Fourier sequence. And of course, this is deeply connected to the reflections of to the tessellation of modular domain. What is shown here is the following. You have upper half plane, complex plane, and you have triangle which has 0 angles. So it looks like that, this and again. And then you take a center of this triangle and you make a reflection. So you, okay, or better to say, okay, you take this point. So this is the center of the triangle. And then you make a reflection and you get the triangle, which is the first image, which is this one, this, and this. Yeah. So, and then you look how the centers are translated to each other. If you take some corners, you immediately can see that the sequence of triangles are related to appear, so they appear just as these Fourier sequences. So, for instance, reflection first this and then this generates 1 over 2, then 2 over 3, and then 3 over 4. Okay, so now what is the relation with our picture? So I will not prove that, but believe me that the position of these maxima of these peaks are exactly located at Fourier numbers. So this is 1 over 2, 2, 3, 3, 4, and so on. 1 over 2, 2, 3, etc. So, for instance, if I consider the main series 1, 2, 3, 4, 5, etc., this is the series of consecutive reflections. This one, this one, this one, this one, this one, and so on. Okay, so now we know the positions of eigenvalues, but how to compute the degeneration? And this is slightly more tricky. It deals with resummation of this function, but let me just show you the answer. The answer is the following. Let me draw such table where so this is the regular first quarter of the lattice, of the square lattice, and to each line of points I associate the weight. To all points here I associate the weight p in power 0, to all here p in power 1, p in power 2, and so on, etc. And now what I do, I take some value, for instance 2/3, which is just this peak, this position. It's located at cosine 2 pi over 3. Okay, 2/3. So this one, I consider this as a rational tangent, and now I I emit the ray from 0 with this tangent on this lattice, and then I count the points which I meet on this way. So and it will be 0 plus p squared plus p in power 5 plus p in power 8 plus p in power 11, etc. till the infinity. Since p is less than 1, of course, this is convergent function. So, and for each such tangent, I compute this series, and this series is nothing else as just the amplitude of this function. So, for instance, I have series here. They are the same, but these are different values. Here is p 0.9, here is 0.5. So, and for each lambda, for each position, I compute, for instance, pi over 2, I compute this 1, 3, 5, 9, etc. If I return back, so this is 1, no, not this one, 1/2. 1, 3, 5, 7, 9, etc.
Here's a time reminder. You have reached 52 minutes. Okay.
Okay. Good. Thank you. So, and this is related to some function which is known. This is so-called Riemann raindrop function. So, how it's constructed? So, it's just 1/n if x is rational. So, and it looks like that. So you can find it's known as Riemann function or Euclid orchard, and the answer is that this function can be expressed in terms of exactly in terms of this function, orchard function, but there is something more behind. In 5 minutes, I will try to explain, because there is a regularization of this function. So this function can be regularized, and this regularization is shown here. First, pay attention to this figure. So these are the same point as shown here. These are the same point as shown here. Yeah, but the lines are the values of the function computed in such a way. So what is eta? And eta is the Dedekind eta function, so the modular function. The fact which I leave behind is that this picture reminds, and in fact coincides with the stability diagram of Thouless fractional quantum Hall states. So, and you can see the similarity, but there is more physics behind. So what is how this can be computed? So the Dedekind eta function is written here, and it has modular properties which are very well known. So, and we can define the modulus of this function. as shown here, and the picture is drawn here, and this is the top view. The main message, which probably I already have mentioned, is the following. This function can be written as a limit of the following function. So we take, either we can compute this sum, or instead of that, we can compute the analytic, we can take the analytic function, which is function, the Dedekind eta function. And here is the different pictures computed by different ways. Here is just the Monte Carlo simulation of this spectral density. This is numerical summation of this series, and this is the analytic expression of this formula. So connection with stellar taxis, unfortunately, I have no time to mention, but just let me briefly tell what should be the relation. So what is phyllotaxis? Probably let me remind in one word. So if you have the pine or pineapple, so then you can compute how many spirals you have on each fruit, for instance, here. And if you can, if you take different fruits, it's always, this function is always one of Fibonacci numbers. This number is always one of Fibonacci numbers. And there is a question why nature knows that it should be Fibonacci numbers. And it was the nice guess, nice model by Leonid Levitov, who tells that one can consider the following model. Let us consider the cylinder, and let us put the particles on this cylinder. And these particles can move, can slide along the cylinder, but cannot escape from it, and they are repulsive. So if we have the fixed shape of the cylinder, so they form the lattice. But now let us just squeeze the cylinder, keeping the radius, like here. And then what will happen with this new lattice? The particles will rearrange, and this rearrangement will happen through some bifurcations. And these bifurcations, the stable structure of lines is related just to the Fibonacci, is controlled by the Fibonacci numbers. Why is so? Probably I will leave the answer open, but let me just mention that what is the connection with the ultrametric structure of random operators I have shown before. One can write the potential in conformally invariant way. So the potential is just taken as a Gaussian. So this is the potential on the cylinder, and then I make the conformal transform of the cylinder on the plane, onto the plane. So, and then if I consider beta, the temperature, rather small, so then this sum of exponents would behave like that. So this is just the typical behavior of this sum. And as you can see that this structure again resembles much the structure of random operators, spectral density of random operators, as I discussed before. But now this is a metric space. And since we now have the connection between such structure and its analytic expression in terms of modular function, we can consider this transformation of the lattice as the dynamics of some imaginary particle in the relief, which is constructed by such in this special function. So I can show you. So this is this three-dimensional relief, and the typical and the dynamics of the particles in this relief happens along the geodesics, and the longest geodesic, which is open, all other are closed, which starts and ends on the boundary, is just the geodesic which runs through the Fibonacci number. Here is this value, terminal value of golden ratio. Okay, so probably it's very sloppy because I should just very run fast, but let me just stop at this moment and tell you that to my point of view, there is an interesting connection between anomalous statistics with the scaling non-Gaussian behavior and H states of random operators in with Poissonian distribution, as I showed you, and dynamics of particles and stable states of lattices in the geometry as I have shown here. Okay, so I think I should stop now. I have finished.